Assalamualaikum dan salam sejahtera. Hari ini kita akan melihat contoh pengiraan berkenaan dengan axial pump. Selalunya axial pump boleh digunakan untuk kedua-dua keadaan, sama ada bendali tersebut gas, udara ataupun bendali tersebut adalah cecair. Di dalam soalan ini kita akan menggunakan udara sebagai contoh bendali tersebut. An axial flow fan has a half diameter 1.5 meter and a tip diameter of 2.0 meter. It rotates at 18 radian per second when handling 5 meter cube per second of air. Develop a theoretical head equivalent to 17 millimeter of water. Determine the blade outlet and inlet angle at the hub and at the tip. Assume that the velocity of flow is independent of radius and the energy transfer per unit length blade is constant. Take the density of air as 1.2 kg per meter cube. So di dalam soalan ini kita akan menggunakan axial pump, yang menggunakan air ataupun yang mengalirkan udara melaluinya. Kemudian di dalam soalan axial pump di sini, seperti yang pernah kita bincangkan sebelum ini, pelajar perlu memahami bahawa axial fan akan ada hub seperti ini, dan di dalam hub ini akan ada shaft, dan di atas shaft ini akan ada kipas. Oleh itu, di dalam soalan ini diberi hub diameter dan juga tip diameter. So, apa yang dimaksudkan dengan hub diameter dan tip diameter ialah, hub diameter adalah diameter for this area, untuk area di sini. Tetapi for tip diameter means the diameter from this point to this point. Okay. And then the idea is, the second one that you need to understand is, in this statement, we have the theoretical head equivalent to 17 millimeters of water. So here, please be careful because our fluid in this problem is air. We have a flow fan here, but the theoretical head is given in terms of water. So after this, you need to change the water head here into the head based on the air calculation. So this is the solution. First, we need to draw the velocity triangle. So let's say we have a blade like this. So and then we could draw the velocity triangle as this one. So this is the actual velocity V1. And then we have the velocity relative to the blade like this. And this is the tangential velocity. And at the outlet here, we will have the actual velocity like this one. So and then we will have the velocity relative to the blade like this one, and this is the tangential velocity. So at the same time, we could assume that this is the flow velocity and this is the velocity of whirl, VW2. And then this is the information that we have. So in inlet, so this is inlet and this is outlet. So at inlet here, we could calculate the theta here as, okay, let's say we assume the theta here as at this situation, at this angle. So we could calculate the tangent of theta is V1 over U1. Then we could calculate the flow rate here. Okay, we could calculate the velocity of V1 here because it is equal to Vf. Okay, I hope you could understand that. The velocity here is actually if we have a tunnel like this, so and then we have a fan, so we could calculate the flow rate here. The Q is actually the velocity of this one, the velocity in horizontal, divide times with the area of this fan, the area of this passage. However, because we have a hub here, so means that the velocity is not moving through the hub. So we need to calculate only the area of this one. So that's why in this calculation, okay, we calculate the velocity of v1 here by using this equation. So and then we could get the velocity here is equal to 3.64 meter per second. So and then in this question, we use radian per second as our rotational speed. So we need to convert the rotational speed into the linear speed. So the conversion is using this equation, U equal R omega. So by using this equation, we could calculate the value of U1 as 13.5 meter per second. So and then we could calculate the tangent hub here, okay, by using this previous equation, and we could calculate that the tangent here is 0.2696, and then it is equal to 15.08 degree. So this angle is actually only at inlet hub, because this calculation is actually, we have here, okay, let's say we have a blade here. You must understand. So let's say, okay, we have a hub here, and then we have a blade here. Okay, so this is the blade. So and then this blade, so we have an okay, let's say I will draw a little bit clear picture of this one. Okay, let's say we have a hub here, and then this is the shape of the blade, and then we have blade like this one. So now we are calculating for this inlet here. So this is the inlet at the hub, and this is inlet at the tip. So and then here is the outlet at the tip, and this is outlet at the hub. Okay, I hope you could understand the location of this one. So this is the angle at inlet hub. So and then we could calculate the angle at inlet tips by repeating the same calculation here, but we need to substitute the value of radius here according to the location. So if this is the inlet tip, so we need to substitute the radius of the tips here. So we could calculate the U1 here is equal to 18 meter per second, and then we could calculate the angle is 11.43 degree. That's why if you observe, if you have time, you could observe your stand fan. So kita ada kipas yang berdiri tu, saya harap awak boleh tengok design blade dia. Awak akan dapati bahawa angle ataupun bentuk kipas tersebut, angle pada inlet, angle pada outlet, pada hub dan juga pada tip akan berbeza. So ini kerana kita perlu menyesuaikan aliran yang terbaik untuk setiap keadaan. Jadi memadai untuk kita hanya mengira apa yang berlaku pada hub dan apa yang berlaku pada tip. Kerana sekiranya awak melukis dengan menggunakan SolidWorks dan sebagainya, SolidWorks boleh automatically akan buat optimum line yang menghubungkan antara dua keadaan tersebut. Kemudian kita boleh meneruskan pengiraan at the outlet here. So we could calculate based on this velocity triangle. We could calculate the angle of theta is Vf2 divided by U2 minus Vwall2. So we know that the flow velocity of flow Vf2 is equal to 3.64 meter per second. We could calculate the U at hub and U at tip here as 13.5 and 18.0 meter per second respectively. So and then, how to calculate the value of Vwall2? Okay, according to the question, we know that the theoretical head is equal 17 millimeter of water. Okay, this is a very critical calculation, because you need to understand that we are solving a problem of air. So means that we need to convert everything using the properties of air. So if we have a 70 millimeter water here, so we need to convert this height into how many millimeters in terms of air. So we could calculate as this one. We just compare the pressure. So we have rho GH for air is equal to rho GH of water. So in this situation, the value of H of water here is given as 17 millimeters. So means we could calculate this using this equation to know what is the value of the height of the air here. So it is equal to 14.17 meter. So what is these two height means? So means that the energy, if you have energy, one specific energy, so the energy who could lift 17 millimeters of water also could lift 14.17 meter of air, because air is less dense compared to water, so means that that energy could lift air much higher compared to what they could lift for water here. So and then we could calculate that from this equation, then we could calculate that the V2 can be calculated like this one, 14.17 gravity divided by U2. So and then we could calculate the value of VF of this one at outlet. So this is the VF at outlet. This is the tangential velocity at hub. So and then this is the V2 for hub at outlet. So and then we could calculate the angle here is 48.7 degree. And this is the calculation for outlet at the tips. So we have VF2 as 3.64, we have U2 at tips here, and then we have V2 at tips here. So and then we could calculate the angle is 19.5 degree. So I hope you could see this calculation, because in axial pump, you need to very careful because you have 4 locations as I said previously. So this is the hub. So you have a blade like this, for example. So you have the inlet at hub and outlet at hub here. So and then this is the inlet at hub, and this is the outlet at this is inlet at tips, and this is outlet at tips. So this is the second example. An axial pump flow operates at 500 RPM. The outer diameter of the impeller is 750 mm and the hub diameter is 400 mm. At the main blade radius, the inlet blade angle is 12 degree and the outlet blade angle is 15 degree, both measured with respect to the impeller rotation axis. Sketch the corresponding velocity diagram at inlet and outlet. The hydraulic efficiency is 87% and overall is 70%. Then calculate the heat generated by the pump, the rate of flow through the pump, and the shaft power consumed by the pump. So in this question, we have the axial pump, and then we have a condition like this. So we have a hub here. So this is the blade. Okay, for example, but we only need to calculate at mean blade radius. So we need just to calculate on the middle point here, not at the hub and not at the tips. So means that you need to calculate what is the radius of this line. So this is the solution. So we know that this is the velocity triangle. So we assume that the 12 degree is like this, and the 15 degrees is like this. Okay, so and then this is all the information. So we have the diameter for tips and the diameter for hub here. Then we need to calculate the average diameter. So according to this calculation, we could calculate that the average diameter is 0.575 meter. So and then we could calculate the value of U by using this equation, U equal pi dn over 60. So we get that the value is 15.06 meter per second. So and then for inlet here, so according to the velocity triangle, we could calculate that the V1 is 3.2 meter per second. So and then at outlet here, by using the angle here, we could calculate the V2 is equal 14.2 meter per second. So and then the actual velocity here can be calculated as 14.5 meter per second. Okay, first question, the head generated by the pump. So we know that the relationship of hydraulic efficiency is power out divided by power in. So the power out here is the manometric head and the power in is the Euler head. So and then we could calculate the manometric head, so means the output of the pump, because head generated here means the output of the pump. We could calculate as this one. So this is the value of hydraulic efficiency is given, which is 87%, and the equation of Euler head here is given as this one. So I hope you could make a revision for your fluid mechanics 2, because we already learned about Euler head in fluid mechanics 2. So we substitute all the value, we could get that the manometric head here is 18.965. So and then we could calculate the flow rate. So again, the flow rate can be calculated by using the simple equation of Q equal A times V. But you must be very careful, because the cross-sectional area here is, if we have a hub here, we have a blade here. So you need to only calculate the area of this one. You need to deduct all the area with the area of the hub here. Because the idea is simple, the flow is not flowing go through the hub. Okay, so we will calculate the equation like this one, and then we could get that the flow rate is equal 1.01 meter cube per second. And then we could calculate the shaft power as this one. So overall efficiency is power out divided by power in, and then the shaft power is power out divided by the overall efficiency, and then we could get it is equal to 268.4 kilowatt.